Okay, so one of the skills you'll really need for this class is scientific notation. And you'll have access to this Nearpod if you think I'm going too fast and you can't write things down. And if you have already a good understanding of scientific notation, that's excellent. I find most students do coming out of middle school, but a lot of high schoolers actually don't use it that much in their high school mathematics classes, so they kind of forget about it. So if this is a little bit too easy for you, just let me know and we can make it harder next time. Essentially, scientific notation is just using powers of 10. And the reason we really need it in chemistry is because some of the numbers are really, really big. Like if you were to count how many molecules in a little spoonful of sugar, it would be a huge, huge number. And then if you were trying to talk about the size of an electron or the mass of an atom, they're really, really small numbers. So we need to be able to use powers of 10 easily because some of our numbers are extremely small and some of our numbers that we'll use are extremely big. So using powers of 10, they could be like positive powers of 10, which means we have one or more power of 10. And again, these should be a little bit familiar. I'm not sure where you guys learn about scientific notation, but again, like 10 to the first power would be just 10. 10 squared is 100. And the exponent just kind of shows you how many times you'll move over a decimal place. So with a 0, we move the decimal place from the 1 0 times. With a 1, we move the decimal place from the 1 1 time. And so on. When we have 10 to the 9th or a billion, we have a 1 and we have moved our decimal place over 9 times from the number 1, that base number. Negative scientific notation does the opposite. It's giving us numbers that are smaller than 1. So again, 10 to the 0 would be 1, but 10 to the negative 1 means I move that decimal place over 1 to the left. To the negative 2 is 2 to the left, and so on. So 10 to the negative 3, moving it 3 places, 6 places, and 9 places for a billionth. So if it is negative, it's a number less than 1, but more than 0. And if it's positive, it's a number greater than 1. We can use these in different places. Like if we were talking about something the size of the moon weighs on the order of 10 to the 22nd kilograms, very large object. An electron, being the very opposite on scale of that, is very, very small, weighing 10 to the negative 28th grams. So very, very big things we need scientific notation for, very, very small things we need scientific notation for. And another way you can do this is something called e-notation. And e-notation is what a spreadsheet would use or what a calculator would use. So I'm not sure what variety of calculator you might have, but you will need a calculator. They have changed it so the multiple choice portion of the AP exam and the free response both are calculator active. So you will be able to use a calculator on the exam. So practice your calculator use. We're going to talk about today are units. This is how you're going to decode problems. So if you can figure out what the number represents, what kind of measurement, then it's really easy to find what formula you need to use and to decode what you have to do to solve the problem. So the numbers in chemistry all represent measurements. There's a few things that don't have like a measurement, like percentages or fractions, but for the most part, every number you use in chemistry represents a measurement that you made somehow or that was made. So they're either measurements that are directly measured in lab, or they're calculations based on measurements, or they're calculations based on measurements that have been standardized and agreed upon by a lot of people. So they're in like a table or something. So when we do calculations with these numbers, we can't have, like with this last example we did a minute ago, we put like 4 numbers in our answer, like 18, whatever it was, 1845 times bigger. But that's more numbers than we had in either of our 2 measurements. So we need to think about how many numbers are in the original measurement, and that lets us decide how many numbers to put in our answer. So in general, this is called significant figures, and you'll have a little bit of practice on this in your worksheet, your homework assignment. But they aren't too picky on the AP exam with significant figures. So if you do take like a high school chemistry class, most of the time high school chemistry teachers are really picky about scientific notation, or not scientific notation, significant figures. But the AP graders are not quite as picky, and people in professional settings aren't always quite as picky about significant figures. So do go through some of the reading on that with some of the different rules. But in general, you're just going to round your answer to the same number of digits that you were originally given in the problem. And you're going to use the smaller of the numbers. So for what we just did, excuse me for a second, I'm going to cough. For this one, the scientific notation doesn't count. So the only digits that matter are the digits in the base, the digits in the coefficient rather. So this coefficient has 3 numbers, and this coefficient has 3 numbers. So when we were putting down our answer, the 1845.303867, we really should round it so there's only 3 numbers in our answer and 1 0. So again, the reason for this, these are called significant figures, is because of looking at the original measurement and how much precision there was for that original measurement. So like this is showing a digital balance, and this digital balance says these 3 marbles have a mass of 23.8 grams. So that balance is kind of precise. It goes to 0.1s, but it isn't like super, super awesome measuring to dozens and dozens of places of a gram. So given that, if the 3 marbles have a mass of 23.8 grams, if I wanted to figure out the average mass of a marble, there was 3 marbles, so I could divide 23.8 by 3. But the problem is I get like this number with a 3 repeating. So I get 7.93 and just keeps going, 3 through 3 through 3. So rather than record that answer, my balance didn't go to that many places. My balance only went to the 10th place. I can estimate one more than what the balance went to, but essentially I'm going to look at how many digits there were in my measurement. So the 20s places, like the 20 is 1 digit, the 3 is another digit, and the 8 is a 3rd digit. So that means it has 3 numbers in it. Now, if we'd have zeros are where we can have, sometimes they count, sometimes they don't count. So the rules get a little more picky, but really just look at how many numbers were in the original measurement. And that's what I should round my answer to. So since there's 3 numbers in this, I'm only going to round to 3 numbers for this. If the number after the number you're rounding to is less than 0.5, you're going to just keep the number the way it is. If the number after the number you're rounding to is 5 or greater, you're going to round it up. And you're probably really familiar with this with grading. Most teachers, like if you have a 0.5 or greater, most grading programs will round you up. So if you had an 88 or 89.5, that would round up to a 90. So the rounded number that I would actually record for that would be 7.93. Again, I wouldn't put all the numbers after the decimal. I would just put the same number of digits that I had in my original measurement. There are some pickier significant figure rules. So if you do take high school chemistry or secondary chemistry, your teacher will be pickier about significant figures, most likely. But the AP graders, as long as it's about the same digits as you had in the original measurement, you're fine. They're going to just be a little pickier. If you like write that 7.9 with all the 3s, they'll be like, nope, you're not getting full points for that. And again, this is just kind of repeating that. There are several significant figure rules, mostly dealing with when a 0 is a significant figure and when it's not. But don't make that a huge focus. You do need to kind of pay some attention to it. So I would read through that when you're reading through the workbook and the reading that I put in Google Classroom. But really, usually scoring is more focused on your process than it is how you round it. So it is important, but it's not the most important thing. Okay, we do have lots of different units that you're going to be using in AP chemistry. Some of these you may be familiar with, some of these you may have never heard before. So I'm sure you've heard of meters, grams, and liters, because those are things we use every day, kilograms, etc. The little number in, or the little letter in parentheses, is what it usually is in a formula. And then the other number in parentheses is what it is as far as the unit. So meters are abbreviated M, but oftentimes if it's in a formula, it has X and for distance. For mass, in a formula, it has a lowercase m that represents mass. But like it said 100, it wouldn't say 100 m because that would mean 100 meters. It might say 100 grams, which would be a lowercase g. So if you're trying to look for mass in a formula, it's going to have a lowercase m, but for the units, it's going to have a lowercase g, or it could be kilograms. We'll talk more about metric conversions next week. For volume, volume in a formula is going to have a capital V, but the unit we measure volume in is liters or milliliters, which would be, again, a metric conversion. So liters are milliliters, and it's a capital L for liters. Temperature is always capital T in a formula, and the two units we're going to use in chemistry are Celsius, but more often we'll use Kelvin. So Kelvin is good because it doesn't have any negative numbers. So there's no negative Kelvin number, so that makes it easier to do proportions, which we'll need for gas laws. So Celsius you're used to, so we measure the temperature outside in. But Kelvin is just that Celsius temperature plus 273. So we don't end up with any negative numbers. And you won't need to use Kelvin until we get into gas laws. Pressure is another unit, and it has lots of different things that can stand for pressure. There's a lot of different units. The one that's the true metric unit is Pascal, because it takes into all the other units kind of combined. But you may also see atmospheres. And that one kind of is more logical because there's one atmosphere above us on Earth. So 1 atmosphere of pressure is our typical pressure. And it could be in millimeters of mercury. So if they talk about barometric pressure on the news, when you're watching the news or watching the weather, they may talk about millimeters of mercury. And if you're listening to some stations, they may even use inches of mercury. And there's also bars and all kinds of other units for pressure. It's essentially how much weight there is per how much area. We're also going to learn about a concept called moles. Moles are an amount of something. We use a lowercase n in a formula. And we use a lowercase n pretty much if we're talking about moles and any other thing. So it's just going to say moles typically written out. Or it may just be MOL instead of MOLES. But the number of moles is just N for number. Energy, there's a whole bunch of forms of energy. They're all measured in joules. So joules are the units for energy, but there's lots of different formulas for energy. The two we're primarily going to use is Q for heat, and then H is for heat of reaction. There's also kinetic energy that's in joules, and there's also potential energy that's in joules. And we'll also learn about rates, like how fast something happens. So we'll use time. And times units are either seconds, minutes, or hours. And it's always a lowercase t. So if you see a lowercase t in a formula, that's for time. If you see an uppercase t in a formula, that's for temperature. But my clue is that that little g means it's a mass. That's a gram. And this ml has liters in it, so that's a volume. So my grams, little g tells me it's a mass, which is m in a formula. And then with liters in it, that means it's a volume, which is capital V in a formula. So the numbers I will plug in is 100 grams for a mass and 62 milliliters for my volume. Anytime it says the word per, that's another part of decoding a problem. That word per means divide. So this word per, you need a formula. The formula for density is mass per unit volume. So I'm going to put in my 100 grams for my mass and the 62 milliliters for my volume. When I put that in my calculator, I get 1.612903. But remember my numbers in here, I only have 2 numbers for this. Putting a decimal after this tells me that there was exactly a 100 grams. So that decimal tells me it was exactly. So I use the one that has less precision. 60 only has 2 digits, 100 has 3 digits, and that decimal tells me if it was exactly those 3 digits. So I'm going to round it to the smaller one, which is 2 digits. So round it to 1.6 to match the one that's the less precise measurement. Units to decide what it is, and then find a formula for it. And the units don't go away when you divide it. So it's still going to be grams and it's still going to be milliliters. You're not going to have it like disappear when you do that. Units are very important. It tells you what was measured and what that represents. And if you do put in numbers without units, there is a good chance that you won't get points on a particular response. So always make sure that you do put your units, and if it specifically says in a problem, an AP exam, give the answer with units. They won't give you credit unless you have the units there. And we look at the letter that's after the number, decide what it says 10,000 and has a J beside it. So J's are for joules, which is energy. So I know in my formula, I'm going to have one of these symbols for energy. And then again, I have little g, and little g is a symbol for mass. So it's grams for mass. And then the formula, I'm going to look for something that has an M. I'm going to look for a formula that has either Q, Ke, H, or Pe. I'm going to look for a formula that has M in it. Specific heat is a constant for a pure substance. And that would be like given to you in a formula that has a C that stands for specific heat. And that'll be something we talk about more as we get into some of the topics in the fall. And then in this case, this degree C is for a temperature. So I need a formula that has M, one of these, C, and T in it when I'm looking at my formula sheet. I'll show you guys that in a second, because I'll link it in Classroom so you have a copy of it. Okay, so taking my numbers, my J is 10,000 joules of energy. My G, which is a mass, is 100 grams. And my specific heat, it says, is 4.18. Now you notice that this has a bunch of units in it. Well, think about what we just said for density. For density, the grams and the milliliters both stayed in the unit. So that means this is a kind of comparing all of these units. So specific heat is actually the amount of heat it takes to raise 1 gram, 1 degree Celsius. So I don't have 1 gram, and I'm not going to raise it 1 degree Celsius. So it's going to be a different amount of energy. And then when I have a change in something, this little triangle symbol stands for change. So it's called a delta, and delta is the symbol for change. So I don't need to just have T in my formula. I need to have a delta T. So again, trying to decode the problem, the key is looking at the units and what each thing stands for. So if I look at my formula sheet, there's a formula that has Q, M, specific heat, and delta T. So I just plug each number in where that letter is. So my Q is where the joule number goes. My M is where the gram number goes. This little CP, or specific heat, is where that number goes. And then the unknown, I'm going to just leave as a letter. I'm going to leave it the letter it is. So the first step is to just plug the numbers in. So just plug the numbers into the formula. And then I'm going to multiply these two. And when I multiply 100 grams times 4.18 joules per gram. Gram is going to cancel out because I'm dividing grams by grams. And that means I'm going to be just left with 418 joules per degree Celsius after I multiply these two numbers together. And when they're written beside each other in a formula, that means you multiply them. So if it's this and this and this, all those symbols written next to each other, that's multiplying. If you're supposed to add something, it'll specifically have a plus sign in there. So these are multiplication. So now that I multiplied 104.18 to get 418, I'm going to divide both sides by 418 joules. So it's going to be over 418 joules per degree Celsius, and that'll cancel that out. And then this side over 418 joules per degree Celsius. And that's going to cancel out this unit. The joules will cancel out when I divide joules by joules. So units can cancel out if you divide by the same unit. So 10,000 joules divided by 418 joules per degree Celsius gives me a degree Celsius. The joules cancel out and I'm left with 0.029 blah, 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 all that number. So after I've done that, gone through the 0.0239, da, 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 that is my delta T. That is the change in temperature. And also it's helpful to see what question it asks. What is the change in temperature? So that amount of energy didn't change the temperature very much. The process that I want you guys to focus on is not specifically solving this kind of problem, because we're going to work on these a lot more later. It's just looking at the units and trying to figure out what is that standing for. That's the skill I want you guys to focus on, saying that joules are energy or grams are a mass. Those kinds of things, or degrees Celsius is a temperature.